A diesel engine does not produce smooth rotation by magic. Each cylinder delivers a short combustion pulse. The crankshaft converts that downward piston force into torque, while the flywheel stores rotational energy between pulses. Counterweights control rotating and reciprocating inertia forces. The crankshaft still twists elastically under every firing event, so a torsional damper protects it from resonance. Engine mounts then isolate the vibration that remains. In this Aspling machine rescue lesson, we will follow the complete force path, explain what keeps the crankshaft turning, show what makes an engine balanced, and diagnose what happens when any part of that system is wrong. Combustion pressure acts on the piston crown. That pressure creates a downward force through the wrist pin and connecting rod. The big end pushes on an offset crank pin, not on the crankshaft centerline. Because the force acts at a radius from the shaft center, it produces torque. Near top dead center, the lever arm is small even though cylinder pressure can be high. As the crank rotates, the lever arm increases and useful torque rises, then falls again later in the stroke. The connecting rod also pushes sideways on the piston and liner. The crank mechanism therefore converts reciprocating motion into rotary motion, but it also creates changing bearing loads and vibration forces. A four-stroke diesel completes one cycle in 2 crankshaft revolutions. Only the power stroke adds substantial energy. The intake stroke consumes pumping work, the compression stroke absorbs stored rotational energy, and the exhaust stroke uses energy to push gas out. During compression, the crankshaft and flywheel slow slightly. After combustion, they accelerate slightly. The starter first supplies enough energy to compress the air and reach firing speed. Once running, one cylinder's power stroke helps carry other cylinders through compression, gas exchange, friction, pumps, and accessories. The governor and fuel system control average speed by changing fuel quantity. The flywheel smooths the short-term speed change. It does not create power and cannot carry an overload forever. In a multi-cylinder engine, the crank throws and firing order space the power strokes around the 720-degree four-stroke cycle. More evenly spaced firing events reduce the time between torque pulses and make rotation smoother. The exact firing order is chosen to manage crankshaft loading, torsional response, bearing load, gas exchange, and thermal distribution. The crankshaft speed is never perfectly constant. It accelerates after each strong cylinder fires and decelerates between events. A weak injector, low compression, incorrect valve operation, or a misfire changes that pattern and creates a combustion imbalance even if the rotating assembly is perfectly mass balanced. Cylinder contribution and mechanical balance are related through vibration, but they are not the same fault. The crankshaft carries main journals on the rotational centerline and offset crankpins for the connecting rods. Crank webs join those journals, counterweights oppose the crank throws, and generous fillets reduce stress concentration. Oil drillings feed the connecting rod bearings through the shaft. The front nose drives gears, pulleys, and the torsional damper. The rear flange carries the flywheel. Main bearings support combustion and inertia loads while thrust bearings control axial movement. A crankshaft must resist bending and torsion millions of times. Surface finish, journal geometry, fillet condition, hardness, oil supply, and correct bearing clearance all matter. Grinding into an incorrect fillet or blocking an oil drilling can destroy an otherwise good rebuild. The flywheel is a large rotating mass mounted at the rear of the crankshaft. Its resistance to a change in speed is called moment of inertia. Mass placed farther from the center contributes strongly, which is why the heavy rim is so effective. Rotational energy increases with inertia and with the square of rotational speed. After a combustion pulse, the flywheel absorbs energy as the assembly accelerates. During compression and between power strokes, it returns energy as the assembly tries to slow. This reduces cyclic speed variation, improves low-speed stability, and helps the machine accept sudden load. But more inertia also slows acceleration and deceleration. The correct flywheel is therefore part of the engine and driveline design, not simply any heavy disc that fits. Balance starts with the center of mass. A rotating assembly is statically balanced when its combined mass center lies on the rotational axis, so it does not always roll heavy side down. Dynamic balance also corrects an end-to-end couple. Equal heavy spots at different axial positions can create a rocking moment even when static balance looks acceptable. The crankshaft, damper, flywheel, clutch, or coupling may be internally balanced as separate parts, or an engine design may use external balance where specific offset mass is built into the damper or flywheel. Never assume interchangeability. A mismatched, externally balanced component can create severe vibration immediately. Balance holes, factory weights, and clocking features must be preserved exactly as designed. Counterweights are positioned opposite the crankpins. They balance the fully rotating portion of the connecting rod and reduce the force that the crank throws apply to the main bearings. They can also offset an engineered percentage of reciprocating mass, but a piston moves up and down while a counterweight moves in a circle. Trying to cancel all piston force with rotating weight would create an unwanted sideways force. The design is therefore a compromise based on engine layout, speed, stroke, rod length, bearing loads, and crank stiffness. Replacement pistons and rods must stay within the specified mass grouping. Removing metal from a counterweight, fitting one heavy rod, or mixing piston assemblies changes dynamic bearing loads, even if the engine can still be turned by hand. Engine layout determines which inertia forces cancel naturally. In a conventional inline-six, piston pairs move together and the crank arrangement can cancel primary and secondary shaking forces and their end-to-end couples, giving excellent inherent balance. Counterweights are still required to manage crank and bearing loads. A conventional inline-four cancels primary vertical force, but its pistons accelerate faster near top dead center than near bottom dead center, leaving a second-order vertical force. Some inline-fours use two contra-rotating balance shafts with eccentric weights, timed at twice crankshaft speed, to oppose that force. Other layouts use different crank angles, bank angles, counterweight strategies, and balance shafts. Exact timing marks are critical. A balance shaft timed incorrectly adds vibration instead of removing it. Mass imbalance is not the same as torsional vibration. Each combustion pulse twists one crank throw ahead of the loaded flywheel and driven equipment. The steel shaft behaves like a torsion spring. It twists, rebounds, and sends an oscillation along its length. At certain engine speeds, the firing frequency can align with the natural frequency of the crank train. Resonance then multiplies twist amplitude and stress, even when the engine feels reasonably smooth externally. The highest fatigue stress may occur near a fillet or a nodal region rather than where the vibration is easiest to feel. Torsional vibration can disturb gear drives, valve timing, accessory drives and bearings, and can eventually crack the crankshaft. A flywheel smooths speed fluctuation, but it does not replace the tuned torsional damper. The crankshaft torsional damper is normally mounted at the front, where torsional amplitude is often high. In an elastomer damper, the hub follows the crankshaft while an inertia ring moves slightly out of phase through a bonded rubber layer. Rubber shear absorbs and dissipates vibration energy. In a viscous damper, a sealed housing follows the crankshaft while a free inertia ring shears a thin layer of silicone fluid, converting oscillation energy into heat across a broad operating range. Both are engineered for a particular torsional system. The damper is not merely a pulley, and its inertia ring is not automatically the crankshaft's external balance weight. Heat, age, oil contamination, impact, rubber cracking, ring movement, housing dents, or fluid leakage can remove its protection. Several components control different parts of the vibration problem. Counterweights reduce rotating and bearing forces. Balance shafts cancel selected shaking forces. The torsional damper limits crank twist. The flywheel smooths cyclic speed change and stores rotational energy. A flexible coupling, clutch damper, torque converter, or dual-mass flywheel can reduce torsional vibration entering the driveline, depending on the application. Engine mounts isolate the remaining motion from the frame and operator. None of these parts can compensate indefinitely for a misfire, bent crankshaft, loose flywheel, incorrect component, failed bearing, or mistimed balance shaft. Replacing soft engine mounts may reduce what the operator feels while the damaging source remains. Always separate source control from vibration isolation. When balance or damping is lost, the evidence can include a strong once-per-revolution vibration, a second-order vertical vibration, changing vibration through a narrow RPM range, belt slap, pulley runout, loose bolts, cracked brackets, flywheel fretting, seal leaks, abnormal main bearing wear, gear noise, or crankshaft fatigue. First, confirm when the vibration occurs. Engine speed, load, temperature, gear selection, and accessory engagement. Use a tachometer reference and vibration analyzer to identify orders rather than guessing from feel. Compare cylinder contribution to separate combustion imbalance from mass imbalance. Inspect damper witness marks, rubber position, cracks, dents, bulging, and leakage. Check flywheel and coupling bolts, runout, crank end float, main alignment, journal condition, piston and rod mass groups, balance shaft timing, and mounts. During repair, treat the rotating assembly as a matched engineered system. Record component orientation before removal. Keep matched rods, caps, and pistons together, verify part numbers and mass groups, protect journal surfaces and fillets, clean every oil drilling, and measure crankshaft runout, journals, thrust clearance, and bearing geometry with the exact OEM limits. Fit the correct damper and flywheel, preserve dowels and clocking, use specified fasteners, lubrication, torque sequence and torque angle procedure, and time balance shafts exactly. Rotate the engine manually before starting and investigate any tight spot. Never hammer a damper onto the crank nose or pull it in with the retaining bolt unless the OEM procedure specifically permits it. Control stored rotational mass, lifting hazards, and pinch points with approved tools.